and I'm in the Department of Electrical Engineering and Computer Science. And I'll be talking to you today about a project that two of my students and I did. Actually, most of it was in 2006, but it's gotten some press lately because stuff hasn't broken as a result. So that's all I was going to do. So what we did was an analog chip, and analog electronics are used in very critical places within space avionics, including power systems, guidance, navigation, imaging, vehicle health monitoring, and also some of the scientific instrumentation that's required in the studies of materials and so forth. For example, on Mars. These electronics have to be radiation tolerant, low power, very robust because you can't easily get up there and fix it, and a very long operational life, and all under the extreme environmental conditions of their space environment, in this case, Mars. So real quick, analog, and it's typically contrasted with digital. Analog has to do with these continuously variable signals. Those are the kinds of signals that analog circuits process. Digital circuits, they have discrete levels, and these represent various bits. But let's be clear, the world is analog and digital is just convenient. A couple schematics, no fear, I will not get serious about these, but this just has to do with the fact that this was an op-amp, a chip that had 4 op-amps on it, operational amplifiers, and this is just, it has a bunch of very important characteristics because it's ubiquitous to electronics. You can't really do good analog systems without them. They're vital in analog systems. So Curiosity specifically needed op-amps, and therefore 2 of our quad op-amp chips within every motor actuator control module, and you can see this depicted over here, each one of these control modules, and each of those green little circuit boards is about 1 inch by 1 inch an inch. So very compact cube there. And JPL couldn't find any of these to work within the commercial off the shelf. We had the opportunity, not because of the football program, but because I was the lead of the analog consortium, the University Consortium for Extreme Environmental Electronics, the analog lead for that at JPL. And again, Curiosity needed over 90 of these to implement the system. Now, this Martian environment, temperature swings from -120 to 20 degrees C. Some people would argue down to -140 degrees C. Also light atmosphere and some radiation. So it's a tough place. Property values are still cheap. Get in while you can. I was hoping that, okay, good. So mission reuse. This JPL, it wasn't enough just designed for Mars. They want the biggest bang for the buck. So we want to reuse this for a bunch of missions, and so that included expanding the temperature range, required expanding the temperature range for the chip to -180 degrees C to +120, so they could send it to asteroids and maybe to the moon and all sorts of cool places. And of course, reliability is a huge challenge because again, difficult to go up there and fix it, so it had to be reliable by design. Mars in particular is tough because of the cold conditions, predominantly cold conditions. Cold actually exacerbates hot electrons, which is a predominant device performance and degradation mechanism in electronics, silicon-based electronics. And we also had to be amenable to what was already there within their electronics. So we had to adapt to 5 volts, even though they wanted the manufacturing technology to be 3.3 volts. That is to say, 3.3 volt technology is newer than 5 volt technology. And that meant additional voltage stress that we had to contend with. How we pulled it off, we had to be very careful. The simulation of our circuit, the models provided by the manufacturing vendor only covered the Earth-based military spec range of -55 to 125, so we had to extend that and then validate it through characterization of test devices over wide temperature. And that simulation, and developed a new simulation methodology new to us that we had never done before, using safe operating area, these parameterized that would monitor voltage stress across each transistor, and there's well over 100 transistors within each op-amp itself, and again 4 op-amps on the chip. And a new biasing strategy, and this led to a key innovation for this work. All the conventional biasing approaches for analog wouldn't cut it. It required too much performance compromise over this very wide temperature range, the 300-degree swing, if you will, for the specification. And so here's another technical slide, double E. There has to be a schematic and some math. But basically, the personality of each transistor or device is quantified by a thing called inversion coefficient, and we found a way to maintain constant transistor personality over very wide temperature, and that was a huge innovation by one of the students, led to a patent. And we also developed clever circuit topologies themselves that would manage voltage stress over both dynamic and static conditions. And so that was a key important innovation also that made this work out to be reliable by design. A key result, the Jet Propulsion Laboratory successfully flight qualified the chip. That's a very exhaustive process. So this is the part where you say, bazinga. Thank you. And the chip is just under 3 millimeters by less than 2 millimeters. The artwork was there on the side, on the right. The student, one of the students, Robert Greenwell, he ended up getting his master's thesis out of this, also some papers, a book chapter, but only one patent because it's not a referee publication, would not help me get tenure, so I only did one patent. So student success is really the most important result from all this, the knowledge and experience that they gained through this. Stephen Terry is now graduated UT PhD. He's actually my first PhD grad here at UT. He's now at Texas Instruments Dallas. He designed the chipset that lets you set your cell phone down on a pad so it can recharge without hooking it up to a cable. Yep. And Robert's working in North Carolina. And what was really cool, this generation of students that followed him in my lab, they ended up doing a summer internship at JPL a couple of years ago. And they were hanging out with JPLers when Curiosity successfully landed and woke up. Now that's just awesome. And so the students got to experience that, and it made them all very proud, of course. And I want to point out that, you know, it's a 500 mission day expectancy. The Curiosity's well exceeded that already. There's been no angry phone calls. That is a wonderful thing. Engineers are the first to get thrown on the bus, by the way. And that has not happened. So thank you very much for your time and attention.